All right, we're going to take what you know about exponents at this point and also what you know about radicals, and we're going to put the two together. And we're going to talk about rational exponents. And so the exponents we're going to be looking at are similar to what you see here with these key concepts. They're fractions. Some of the fractions will have a 1 as the numerator, so this is like 1/2. Some of them will be other fractions like 2/3. Your m and your n are positive integers, so think about what that means, positive integers, and a is a real number. Now, when we talk about the nth root of something, you all are used to taking the square root. So if I ask you what's the square root of 25, you know the answer is 5. What you don't realize a lot of the time is that the n here, when I talk about the nth root, this is actually an understood 2 whenever you talk about the square root. Basically, you want to know what number times itself. So you have the number twice, that's why there's a 2 there, gives you 25. That's where the 5 comes from. I could break 25, say a were 25. I could break that into 5 times 5. So that gives me two numbers that multiply together that equal 25. Now, keeping in mind the number has to be exactly the same. So 5 two times gives you 25. All right, so square root, you're used to taking that. But what we're going to talk about are other roots, third root, fourth root, fifth root, that sort of thing. So let's look at just this example here. If this were 1/2, 1/2, okay, the index gives the degree of the root, okay? So n is your index. That tells you the degree of your root. Obviously, the sign is the radical sign, and a is called the radicand, okay? So if I have 25 to the 1/2 power, basically what I'm saying is 25 is my radicand and my denominator is my index. That tells me what degree of the root. So I want the square root of 25, basically is what 25 to the 1/2 power would be. Now, with m over n, when you have fractions like 2/3, something like that, the denominator, the n, is still your index. But the m, which in this case was 1, and we know anything to the first power is itself, so we didn't have to put the 1 there. But in this case, if I have an m, that means I have something other than 1. That becomes my exponent on my a, or you can write it and have the nth root of a in parentheses and then raise it to the power of m. So it just depends on how you write it. You could raise the radicand to the nth power m first and then take the nth root, or you could take the nth root of a and then raise it to the power of m. We're going to look at a couple of some examples here to help, but these are the general rule here for radicals and rational exponents. We're going to apply those here to some examples. So let's look at this first one. I have the third root of 125. That's what the 3 means, the third root of 125. So we're going to look at one method to solve this. Method 1 is how many, basically you've got the degree of 3. So I need 3 numbers here that equal 125, and the number has to be exactly the same. I can't just pick 3 random numbers. So notice if I do 5 times 5 times 5, if I write out 5 3 times, that gives me 125. So that means the cube root of 125 is 5. 5 times itself 3 times gives you 125. So that's one method, is to actually find the cube root of 125, actually find that number 3 times that will equal the radicand. Now let's look at a different method here. This one is the fourth root of 16. Now, you can find these in your calculator. Those of you that have graphing calculators, if you hit the math button, you'll see cube root and you'll see x root. That just tells you can pick any x you want. For those of you that have scientific calculator, you have to hit the second button and you'll see the x root below where your square root symbol is. And the x indicates you just put in whatever root you want and then hit that key and then type in your radicand. But to actually find this is method 2. This is actually using the exponents, the rational exponents. The exponent on 16 is 1, and remember 4 is our degree, our index, and that's our denominator. So that's where the 1/4 comes from. The exponent on 16 is 1, 4 is our denominator. So 16 to the 1/4 power is actually what the fourth root of 16 is in exponent form. And then you want to figure out 16 4 times. What number, well, not 16 4 times, what number times itself 4 times gives you 16? And in this case, it's 2. 2 times 2 times 2 times 2 would give me 16. So what's a fourth of 4 twos? Well, just 1 2. So 2 is the answer there. Okay, so 2 methods. You can either write it out in radical form or rewrite it in rational exponent form and solve. So now it's your turn. I want you to look at this example. This is the cube root of 27. So I'm going to give you some answer choices. Pause the video and go through, try to answer this problem. And you may have used your calculator, that's fine, but the answer to this one is 3. So what number times itself 3 times would give you 27, and that is 3. Okay, just to kind of look at the solution page that they have here. Here's method 1, writing out the 3 times. Method 2 is rewriting it in rational exponent form, finding the 3, and then obviously a third of 3 threes is just 1 3. So that's your answer. All right, now this does get a little more difficult, especially when we start factoring in variables. This one, we've got 12 times a to the 2/3. Now, this is kind of going back to when we had negative exponents and stuff. Look to see what is attached to the rational exponent. And in this case, only the a is attached to the rational exponent. The 12 is just a coefficient out front. So I'm going to bring this up. Let's focus piece by piece. Don't jump through everything here. But what we want to do is we want to, in radical form, do you use the numerator or denominator as the index? Keep that in mind. You use the denominator as your index. That's the degree of your radical, so of your root. So 12 does not have the exponent, so it's still our coefficient up front. 3 is my index, so it's the degree of my root. So then I have my radical sign, and then a to the second power is inside, is my radicand. Okay, so just break apart my rational exponent. Denominator is your index. Okay, so that's pretty simple. That one wasn't too bad. Now, if we look at this one, though, this one has 64a in parentheses raised to 4/5. So that means the 64 is raised to the 4/5 and a is raised to the 4/5. So this one's going to get kind of confusing. So when I bring this up, please focus on one step at a time. All right, since 32 is the 5th power of 2, so basically what that means is 32, you can get that by multiplying 2 by itself 5 times. And the 5 comes here. That's our index, remember. We're going to rewrite 64a as the product of 32 and 2. Now, the reason we did that is because 32 is a perfect 5th root. Remember, we've looked for perfect squares before, 25, 36. Those are perfect squares. This is a perfect 5th root. That's why they picked that number. 32 goes into 64 2 times. So it's kind of like dividing and having your remainder here. But so we broke 64 into 32, or 64a, excuse me, into 32 times 2a. And then we're going to follow exponent rules. When you have a product raised to a power, you distribute that power to each one of the factors. Now we're keeping the 2a together because we just broke it into 2 factors here, 32 and 2a as 1. So 32 gets raised to the 4/5 and 2a gets raised to the 4/5. Okay, power of a product. Now, you rewrite 32 as 2 to the 5th. Now, the reason why we do that is because we just did that on purpose up here. We know that 2 to the 5th power is 32. Okay, really the reason you're doing this is just another way to do this. You could actually go ahead and do 2 to the 5th power, 2 to the 4th power, and then take the 5th root of that. You're going to get the same answer, but this is just a different way to do it. 2 to the 5th power is 32. They just rewrote it. And when you multiply 5 times 4/5, basically that just eliminates your denominator and you're left with 4. So this right here can be done in multiple different ways. This is just one way to do it. Notice they haven't done anything to the 2a raised to the 4/5 just yet. Now 2 to the 4th power gives you 16, so that's where my coefficient up front here is 16. And then they rewrote 2a to the 4/5 in radical form. Okay, 5 is our index on our radical sign, so we put 5 here. 2a is our entire radicand, so it remains in the parenthesis. And the 4th is our exponent, the 4th power. Now, you could actually do all of this under the radical sign and then simplify after that. So like I said, there's multiple ways to do this one. So now I want you to look at this example, and this example is a little bit easier than that one. When you look at this example, you have a to the 5/6 power, and I just want that written in radical form. So I'll give you some answer choices. Pause the video so you can take a minute to look at this problem. Make sure you know which one is your index. All right, so your answer choice should be, you should have picked B. 6 is your index, 5 is your exponent, so that would be radical form. All right, so let's look at another example real quick. This one is converting to exponential forms. This is really easy. Again, 5 is your index, and 3 is your exponent. So when you rewrite this, 5 should be your denominator, and 3 is your numerator. So that, just kind of going backwards, you should be able to do that fairly easily. When you look at this example, this one's a little more difficult. D is what has the exponent here and not the 27. 27 actually has an exponent of 1. It's understood to be 1. So when you rewrite this, the entire thing here, what they did is they took all of this in parentheses and gave it an exponent of 1, which is where the 1/3 came from. And then product to a power, you raise the 27 to the 1/3 and you raise D to the 5th to the 1/3. So 27th gets the 1/3, D to the 5th gets the 1/3, and then simplify. 27 to the 1/3 power is 3, and then when you multiply 5 and 1/3, you get 5/3. Now again, you could raise 27 to the 1/3 power and D to the 5th to the 5/3. You could do this a lot quicker than what they did. If you remember, exponent rules can apply to these radical rules here if you break this apart. So different ways that you could simplify that problem. So I want you to look at this example now, and I know we're kind of going quickly through this, but I want you to get this basic problems down. Change this to exponential form. This should be very simple. Pause the video if you need to. But looking at your answer choices, it should be very easy. Your index is 3, which is going to be your denominator. So it's going to be s to the 2/3. Okay, so going through that quickly, you should be able to go forwards and backwards, and always look in your textbook if you need to review these problems. Now this one, when I read this, it sounds more difficult than what it is. It says you can estimate the metabolic rate of living organisms based on body mass using Kleber's law. The formula R equals 73.3 times the 4th root of m to the 3rd power relates metabolic rate R measured in calories per day to body mass m measured in kilograms. What is the metabolic rate of a dog with a body mass of 18? Well, that sounds so difficult, but it's really not. Basically what it's saying, eliminate all the stuff in here that just doesn't seem to make sense to you. Basically, you've got your formula. R is in calories. That's the metabolic rate in calories. And m is our body mass in kilograms. Okay? Well, they give us body mass. They tell us that this dog is 18 kilograms. So all you have to do is substitute the 18 in for m. Okay, we're just trying to find out the metabolic rate. All right, so put 18 in place of m. Super easy. And then simplify. You have a calculator. You can follow the radical and rational expression rules. Any of that will apply here. Basically, you're taking the 4th root of 18 to the 3rd. So take 18 to the 3rd and then take the 4th root of it if you want to. Or you can use 18 raised to the 3/4 power. That's changing it to a rational exponent. And then multiply that result by 73.3, and this is what you get. So his metabolic rate for this dog is approximately 641 calories per day. So very easy. It looks difficult, but it's not. Pull out the important information, the formula, what each one of the variables stands for, and what has been given to you, and just plug it into your formula. Very easy. All right, so now I want you to try one real quickly. All right, here's your word problem. Again, read it carefully, pull out the important information, and solve for the metabolic rate of a man who weighs 75 kilograms. So here's your answer choices. Pause the video and answer this. All right, hopefully you paused the video. This is your correct answer. And just to give you the solution page real quickly, you're just plugging 75 in place of the m for mass and simplify.